Okay, folks, this is the lecture on rotational kinematics, otherwise known as constant acceleration, otherwise known as rotational physics Sudoku. All right, so Ferris wheel, because we are going to be looking at objects that are rotating. So if you imagine a point on the wheel, so we care about like this person in this, not a Ferris wheel, but pretend like this is the person in the Ferris wheel. Just like they might not have started at the origin, they might not have started at 0 on the unit circle. So this person on the Ferris wheel has an angle theta naught relative to the horizon at t equals 0. The Ferris wheel is rotating counterclockwise, and it's speeding up because the motor's increasing. All right, so bunch of new terms. The math should feel pretty similar because they're the same equations but with different variables. So instead of looking at x, we're looking at theta. The units of theta are radians, and there's a whole table on the next page. Okay, so keep listening to the next page and then go back and forth to decide what you want to write down. This is the lowercase omega, and that's how fast it's moving in radians per second. That's how fast it's rotating. And alpha, like A, is the rate at which the rotation is speeding up in radians per second squared. So a couple of things to note, because the unit circle is defined as clockwise is positive, we are also defining clockwise as positive. It doesn't really matter. That's the standard convention, as long as, just like in left and right definitions of positive, negative, you have to be consistent. So just practice that as we start to do these problems. All right, so this is the chart that you may want to write down that has all of the information on it. Linear kinematics, x becomes theta, v becomes omega, a becomes alpha. Okay, and you can pause and record any of that you want to. All right, so when we did this stuff at the very beginning of the year, not everybody knew calculus, so you might see this on the AP. You're not going to see it on this test because I already gave you in 2024, gave you a test on power that had some derivatives on it. But this is the instantaneous rate of change of a couple of terms. So the angle is changing at an instantaneous rate. That's really the definition of omega. The rate at which the Ferris wheel is rotating, it might be speeding up or slowing down. That might not be constant, so we might want to take the derivative. If we instead just care about the average, then this is an average, not a vector sign. Then you just take the A rock instead of the I rock. Okay, so again, I think this is in the slide deck, because if you are taking the AP, that's classic on the multiple choice for them to give you theta as a function of t, and you take the derivative. All right, and then similarly, you would also take the antiderivative to go backwards one step. And those of you who know integration constants, often but not always, I won't go into the details now, but the initial omega is your integration constant. If you're dealing with polynomials, if you're dealing with something more complicated, that's not true. Okay, we're not going to do that. All right, these formulas should look familiar. This is don't know, don't care with the new variables. This is the fire drill formula with the new variables. I am pretty sure that what I think is kind of goofy is they give you the position function with both linear and rotational, and they give you, I think, don't know, don't care with linear and rotational, which is kind of weird to me because they're the same equation, but I think they still do in 2025. They don't give you the fire drill formula. Super useful formula. Okay. Big fat warning. These equations are only legit if the angular acceleration is constant. You only get a constant acceleration when you take the derivative of theta, the position function. I don't have it. The position function is a polynomial. Okay, so some problems on the AP are plug and chug, physics Sudoku, easy, but some of them, if alpha isn't constant, none of those equations, you can't use those equations. And you've got to use TME at A equals TME at B, or something even more complicated using calculus. That's why your go-to from here on out should always be energy. Okay, even if, just because that's always going to work for you. And the physics Sudoku is not always going to work. And I'll try to warn you as we go off and do these problems, but just be really careful about that. And even if you're not taking the AP, it happens sometimes on the regular test, so please be careful. Okay, now it's time for a question. So I go out and put super cool LEDs on my bicycle, so they're going to go around and around and around. Which point on the wheel has a greater rotational speed? Point Y, where the yellow LED is, or point X, where the blue LED is? Okay, I don't think the answer's on the next page. I think I have to explain it. So it is a trick question. If they have the same, if Y goes around once, then X has gone around once. So if Y has gone through 2 pi radians, then X has gone through 2 pi radians. If Y has gone through 20 degrees, then X has gone through 20 degrees. So it is a tie. And that is why we're going to measure rotation in terms of omega, because everything has the same omega. Okay, so trick question. All right, now question number 2. Which point on the wheel has a greater linear speed? And I'm going to try to be really careful. I'm going to call this tangential speed, because I would say the bike is moving in a line. The center of mass of the bike is moving in a line, but those LEDs are not moving in a line. They are moving in a circle. So what I'm talking about is at any given instant, perfect example with bikes, right? The mud flies off tangent. That's why you have a little fender. If the mud flies off tangent, it flies off with a certain speed. Okay, that's what we call it, the tangential speed. If you remember when we did circular motion, at any given instant, the instantaneous velocity is tangent to the circle. Okay, so if the mud flew off, if a little piece of mud here flew off tangent and a little piece of mud here flew off tangent, which piece of mud is going faster? Okay, this one is not a trick question. The linear speed, even though it's not in a line, but if you tracked that yellow LED and then took that and, laid it out on a line like a piece of string, the yellow LED has to travel a greater circumference than the blue LED does. So point Y travels a greater distance. Okay, so that's why in a race, like in track event, the initial starting position is staggered, or why the speed skaters have to take turns being on the inside and the outside. Okay, so that is the foundations of the variables. And I'm going to stop there to keep it at under 10 minutes. There is a part 2.